This conference will now be recorded.
Good morning and welcome to the Mirabilis Design webinar on making early architecture decisions using system-level simulation. I'm your host Deepak Shankar, and I'll be walking you through a series of examples, methodologies, and case studies that will help you understand how early architecture decisions can impact your product development. As people are flowing by, I will go ahead and get started and not delay any longer. Once again, thank you for attending this webinar. A little bit of logistics before we get started. Everybody has been set to mute. There is an option on the right-hand side in your control panel, which you can click on the orange flower on the top, and it'll open up the entire panel. At the bottom, you'll see a chat window. Go ahead and type in your questions, and there'll be someone in the group that will be answering the questions. With this, I would once again like to welcome you to the webinar, Making Early Architecture Decisions Using System-Level Simulation. I'm your host, Deepak Shankar. A quick introduction to Mirabilis Design before we get started. We've been around for about 15 years. We've got development and support centers in multiple locations around the world. We've got over 40 customers in a variety of applications. As a matter of fact, you can see a number of products shown here that are being developed using VisualSim. The product is VisualSim, which is a modeling and simulation software that comes with a complete package of modeling IP, analysis tools, reports, simulators, and post-processing environments that allow you to do your architecture simulation. The company itself is made up of system architects and folks that have considerable experience in performance modeling. Before I go ahead, I want to first talk about some basic definitions so all of us are on the same page with regards to what it is that we're analyzing. The key term here that we've been talking about, and it's there in our webinar title as well, is architecture exploration. What we're talking about there is really taking the specification that you have developed either on paper or in PowerPoint or Excel and assemble a model such as what you see on the right-hand side, and then run a variety of simulations where you vary, say, things like process speed or bus topology, or put a round robin versus first come first serve in the arbitration schemes for access to different resources. And then you evaluate the timing, energy, cost, weight, efficiency, redundancy, security, all of those attributes to come up with an optimal specification that you can then go build. The whole goal of doing this is to eliminate all the surprises during integration. Another aspect of architecture exploration is that it can be done at the semiconductor level, at the system level, or even at a full network level. The architecture exploration is really for three purposes: performance analysis, power, and functional correctness. Performance is more time related, so it can be sizing buffers, looking at end-to-end delays, what is the effective throughput, and also looking at the utilization or efficiency of usage of different resources. Power is any aspect related to power, primarily around the amount of power consumed per task or power per device, or even looking at spikes in terms of certain shocks that occur that might be translate into like a sudden spike in power consumption. The main idea here is to size the batteries, to figure out what the PV cells should be for, and what is the available power that for your entire design. The last one is functional correctness, which is all about how do you schedule your system. So scheduling can be at an RTOS level, it can be at the bus level, or it can be on the processor pipeline. All of this is really around architecture exploration. The goal is to create a higher quality product. Again, for those joining in new, the control panel on the right-hand side has a chat window. It actually looks like a round circle. If you click on it, you can type in your questions. Everybody has been set to mute, so you wouldn't be able to ask any questions using the voice system. A quick introduction to VisualSim. It's the modeling and simulation software that allows you to do the architecture exploration. It's split into three parts. You got hardware, software, and networks. And the analysis around it is around performance, power, hardware, software partitioning, and failure analysis. The whole goal of the system is to be able to construct a model in a graphical environment using predefined libraries, run Monte-Carlo simulations with variety of traffic, use cases, parameters, and then be able to analyze the results. So the VisualSim Architect provides you the entire platform without having to go across multiple tools and multiple technologies. Before I get started on more detailed explanation, why is VisualSim preferred in the market? And the reason it's preferred is because of the extensive libraries that we provide. So if you look from left to right, it starts off with the more stochastic transaction level modeling. And as you go towards the middle, you see more systems, networks, and finally to more detailed cycle accurate, sometimes spin accurate modeling. So VisualSim covers the entire gambit of tools and technology that is required for you to assemble up your system. Now, what are the design challenges that make architecture exploration absolute essential for your design? Now, before we get started on that, I'm going to move over to the VisualSim modeling environment, which is this right here. What you see is the graphical environment over here. You see a set of libraries. I'm going to open up a new window over here. And what I'm going to do is I'm going to set up certain parameters that allow you to get started. So in this case, we're going to run two different scenarios or construct two different scenarios very quickly. The first one is where I'm going to be generating some traffic. I'm going to be feeding it into a resource, in this case, a server, and I'm going to view the output. So I got three building blocks over here. So I'm going to set the simulation time for 100. I'm going to specify that the traffic is going to be generated every 1 second. And I'm going to generate about 50 of these packets. Or packets are just another nomenclature. We use the words data structure, transaction, request, packets, all of them interchangeably depending on what we're trying to do. We're going to keep all of these the same. We're going to call this the resource. And we're going to say that each transaction coming in is going to be delayed by 1 second. So what's going to happen is I'm going to go ahead and run a simulation. And what you're going to see over here is a series of what looks like a C data structure. This is a transaction that flows through the model. So what you'll notice is some keywords here, which is this was generated at time 0 and it arrived at 1, which is the resource ended up taking 1 second to complete. So it came out 1 second later. And you can also see that it came 1, 2, 3, 4, and so on. Now, what I'm going to do is add some more intelligence where I'm going to specify some details. Now, notice all I'm doing is I'm plugging these in and connecting them up into my system here. So what I'm going to specify here is rather than just giving it a single value, I'm going to give it a range of values. So I'm going to say generate a random number between 0.8 and 1.4. Similarly, I'm going to say, like give it a priority of an integer number between 1 and 4. Okay. Now, in this resource, I'm going to tie those things up. So I'm going to call it input dot time delay, and this one I'm going to say input dot priority. Now, notice I'm not touching this queue number field because I'm just keeping the number of resources to be 1. So what that means is, think about it as if I had 10, that would be like 10 cores or 10 processors or 10 nodes. But here we're just assuming there's only one of those. I'm going to go ahead and rerun the simulation. Now, what's going to be interesting out here, you're going to notice is two things. One is, it's no longer coming in at 1, 2, 3, but they're all coming in at variable times. And you can see what the time delays are because we generated between 0.8 and 1.4. The other thing that you're going to notice is that there's a field called priority. And you notice that each one of them has got a different value. So what ends up happening right here is, initially you see everything coming out as 1, 2, 3, 4, 5, 6. But as I keep going towards the end, you start noticing this. The 50 came out at advance of 34, then 40 came out, 45, and 47. So all I did was specify a range of time delays, and I defined a range of priorities for the incoming transactions. And you notice this block automatically reordered everything, and it figured out what is the way that it needs to be executed. Now, what is this resource block? As I mentioned, it can be a processor, it can be a bus, it can be a network node, any of those kind of things. Exact same design, but what I'm going to do now is I'm going to replace this with something that's very detailed. So I'm going to plug in this one over here. I'm going to bring in a memory subsystem. So I'm going to connect a memory design over here. Connect this up here. And then I'm going to bring in a hardware library component, which in this case, I'll bring in an AXI bus. That's something everybody's familiar with. I'm going to plug that in over there. I'll put this guy right up here. I'll plug in this. So what I've done now is, I had originally just a generic resource, so a transaction model. Now I've taken that same details, now replaced it with an AXI bus, a memory controller, and a cycle accurate cache. Difference is, if you remember in that one, we just had priority, buffer size, the what kind of a scheduling algorithm, and the delay. Now you're going to see a large number of parameters. So that's the transition from going from a transaction level model or more of an abstract model and taking it down to more and more details. So this is, in a sense, how you construct up detailed models in VisualSim. So as you can see, this one here is a model of an aircraft, while another one over here is a model of Xilinx FPGA. So if I go inside of this, this is the entire Zinc Ultra Scale MP SoC. So it's got everything from the 4 Cortex A53s to the Snoop Control Unit L2, all the way down to the DDR. At the same time, it's got all the I/O interfaces, and if you look down here, it's got the programmable logic, which is the actual fabric. So setting up a series of use cases, I can run simulations to evaluate what is the performance when I have 2 of these MP SoCs connected into a single system. So more on that later. But now what I'm going to talk about is a little bit to focus on what are the design challenges that really require a tool like VisualSim or doing architecture simulation. First and foremost is unpredictable timing and behavior, so, or even scheduling. So what that means is, let's take a simple example where we've got 2 processors, could be cores, a DSP and I/O, and you have a task. You see, you have 2 bridges and a bridge and 2 buses between them. So initially, what I'm going to do is I'm going to target only a single task or a single application to run on this. So guess what? You can see that it starts at the I/O, goes to CPU1, goes to DSP, and then comes out through the I/O. So what happens is there's only a limited amount of arbitration or scheduling that happens in any of these devices. Now, what happens if I add another application to the same thing? Now notice there's going to be a lot of contention in all these different devices that are right in the middle. To some extent, even the CPU too is going to, I guess not, but the IO is definitely going to have some buffering as well. So what does that create? That creates some unpredictable activity, and this is really why there's a migration from analytical modeling to more architecture exploration. So what does that mean? If I look at this, I ran it with two scenarios. One was at 200 megahertz and the other was 400 megahertz. As you would expect, 400 megahertz did run much faster, which means your latency, that's the time to go get the data and come back, was lower. Now, it's not 50%, but it was lower by about 15 or 20%. But notice these points which I've circled. What is happening is the system with the faster bus is actually slower. So what are the reasons for these? If you go back to the design, we had a lot of processors and DSPs. Now, because these buses are faster, they're pushing more data into the processors, which in effect is allowing the processor to start buffering more of these transactions. As a result of which, you now have a huge delay that is spiking up over time. Matter of fact, you will see that there are some additional delays that are waiting to spike up if if there's a different sequence of activity that is happening in the system. So this is probably the first reason why you need architecture simulation. The second one is, of course, the software architecture. See, when you're designing your software, you do a lot of things related to scheduling, related to offsetting, related to priority, the time scale, which slot it's going to execute on the processor, all of those kind of things. So what happens is you have varying deadline requirements for different tasks. If you take things like, say, for example, in this case, the automotive system, you're going to have extreme unpredictability because of these a huge amount of data that's going across these networks. And what ends up happening is a combination of sensor data, video, voice, all of these. It's really starting to become very difficult to be able to predict exactly when they arrive at each of the engine control units. The real-time tasks must be assured of meeting deadlines. And this, when you start putting realistic scenarios, it becomes very hard to predict it. And so hence the challenges must be studied in context of the entire system, not a part of the system, not a subsystem, but in the context of the entire system and in the context of power, performance, and reliability. So this is the second issue where you're looking at software task scheduling. The third one, which is far more complicated and probably the next generation, is that looking at innovation, you end up having a lot of unknowns. So it's like, do I go ahead and invest my money on this new technology? Do I invest in RISC-V? Do I invest in building a whole new ecosystem around 5G? What ends up happening is you have a lot of questions. For example, how do I implement my matrix multiplication sequence for an AI versus do I put this on a processor or on an FPGA? The challenges are both exterior and interior. Exterior would be memory accesses, different LiDARs, radars, sensor data input, and also what it's connected to in the rest of the nodes. So some of them may be FPGA based, some of them may be processor based, or within an SoC, there might be IPs, there might be processors, accelerators, a variety of other GPUs, display systems, a variety of these subsystems that might be connected. Interior factors could be things looking at how much of processing does it take to complete each task within an application. What is the connectivity within all of these subsystems? And of course, the biggest one of it is the RTOS isolation in terms of how do I assign tasks to these different RTOS slots, for example. So what are the metrics? One metric can be around certification. The other can be in terms of looking at response time to complete a specific task, like in this case, machine learning. or it can be based on power consumption, or looking at how the redundancy can impact your system. So all of these require a significant amount of architecture exploration that's done upfront, not after the chip or the system is done or after a prototype board is available, but doing it right up front. That's when you can gain complete advantage and complete control over your project. Now that we looked at, what is the motivation to get into architecture exploration, we're going to move over to the next level, which is really looking at what are the different applications of architecture exploration. Architecture exploration can be really looked at as two different segments. There's one at the system level, and then there's one at the semiconductor level. So systems can be looked at like an aircraft, a camera, a radar system, can be a launch rocket, any of those, or even a vehicle, any of those kind of things. Semiconductors can be processors, system on chips, can be specialized devices, can be interfaces, things like Bluetooth or USB 3.0, things like that. Each of them has their own challenges and each of them have their own requirements. VisualSim is one of the few tools where we have solutions that address both of them. So if you look at the system side, to get started at the top level, what you have is really a constellation. So you have a large CubeSat, which has got about 10 or 15 different subsystems, and it has different requirements in terms of meeting the constellation deadlines as to when different tasks are scheduled during an orbit. And then looking at what is going to be the power consumption as a result of all of these different subsystems executing to achieve these different tasks within their specific deadlines. So the goal here is you have these different subsystems, you have these different use cases and orbits, and you want to run different activities within each of these orbits based on a schedule, and you want to see whether they complete within their schedule, or which means they meet their timing deadlines, and or they are within the power budget that's available for the particular design. Now, looking at a much larger or a wider scope of a system is really looking at a network which connects a large number of fast-moving vehicles that could be in 3 dimensions. So in this particular case, what you're seeing is you've got a lot of aircraft, ground stations, and even satellite systems. And you have issues regarding whether I can whether I'm within range, out of range, if there's too much of jamming, so there's a lot of bit error rates that you're looking at. How do you express all of these within a single system? And once you express them, what are the types of analysis you want to do? Is it that I'm looking at seeing how many retransmissions are happening, or am I looking at irrespective of retransmission, I just need to know that it meets this timing deadline and I get so much of throughput within this time period. Depending on that, you would put in different amounts of detail within each of these subsystems. But notice one of the key things is you started off with an aircraft, went down into a lower level, it's got all these sensors, the processing unit. The sensors had its own separate thing, the processing unit had its own, and then you can see the ground system had its own setup. So you can see the importance of the hierarchical modeling, because what is happening here is you have the ability to start defining greater and greater details as you go down the hierarchy. So from a designer standpoint, allows them to put in a lot of details. The other aspect are the parameters. You want to be able to try out different experiments. What happens if I set up my Airlink, which is my processing backplane, from like 5 nodes to 20 nodes? What if I increase my processor from like 500 megahertz to 1 gig to 3.5 gig? What if I change my RTOS buffering? How does this all impact my timing deadline, which is what I really want to achieve? Now, a variety of statistics are required to achieve these. So for example, here, I can look at the latencies. The other thing I can look at is what's the utilization of my different resources, what is my buffer occupancy. I can look at other attributes such as how much of quantity was being utilized out of my passive resources versus an active resource. I can look at those kind of attributes as well. So this is at the network level where you're looking at the overall constellation. From this, I'm going to narrow it down to a behavior model, which is I'm looking at a particular subsystem. So in this case, we're looking at a PLC, which has got a primary system and a standby system, and it's connected through an Ethernet backplane. And there's all these different control devices that have the sensor devices that are connected to it. But we also have a manager or a power, an energy supervisor and a manager in the system. So when I'm looking at this overall subsystem, I've got the processing units here. I got the network topology. I got these sensors that are generating traffic. I got a controller, and I got something that's looking at the power management. So this would be a model that you'd want to construct in an environment like VisualSim for doing architecture exploration. So you'd set up your processor modules, you set up your IOs, and of course the switch manager right here. Now, what does this contain? There's a concept in architecture exploration called behavior to architecture mapping. That is what you're seeing here. So you can see these mappers on the behavior side, which is showing what the connectivity flow of what is the sequence of things that's happening in my system versus the hardware architecture here, which is made up of in this case an ARM Cortex and AXI and a DDR2. So I can actually look at varying, say, the clock speed or varying, some of these polling messages or varying the instruction sequence that's going to be executed and see what happens to my system. So when I look at it, I can also have my IO device, subsystems that are connected over to this processing board, where there's a series of sensors. They have some sort of a polling which goes and gets the data and then sends it out on the Ethernet node and onto the Ethernet network that then gets connected to the back to the processing node. Couple of things you can think about here. One is, I've got a processor, I've got my primary processor and a standby processor. So what happens if the primary processor fails and I have to, switch over to the standby processor? Is it able to work the load? Or I distribute the load evenly across the primary and backup to make sure that they're all working, correctly. Or more accurately, are they able to handle the workload if I distribute them across? So the key things here are I'm looking at some buffering. I'm looking at what my network topology is. I'm looking at what is the processor speed. What are the different tasks that are going to be running on the processor. So I'm essentially defining my entire subsystem right over here. Now from here, I'm going to move over, since we've primarily been looking at this hardware side, move over, talk a little bit about the software. Now, just to remind folks that there is this control panel on the right-hand side with a circle type window, a circle type icon. You can feel free to ask any questions out of that. So if you type the questions, either myself or someone on the system could be answering the questions for you right away. So you don't need to wait until the end of the presentation to do that. Now, going back to the software task scheduling, one of the key things that you might have is be able to accurately describe not just the operating system or the scheduler, or even in this case, a middleware with its own buffer, but also look at the other things like some of your diagnostics, your IO networks, and also the actual processing of my, in this case, runnables, which is a automotive term, but it could be something that's more related to the actual software or the task that's going to be running on the system. So what this allows you to do is allows you to set up what my schedule table needs to be. I can even introduce certain errors and see if the system is still operating correctly, or it identifies some of these diagnostics down here, identify those errors. The last part of architecture exploration on the system side is really related to failure analysis. Now, in this case, what we do with failure analysis is a little unique. We're not focused on failure analysis from a math standpoint of computing the MTBF and MTTR, but rather we trigger different failures into the model and then see how the system behaves. So the main idea here is that I want to replicate, say, a failure where two of the processor nodes fail, or for example, some of the data in the memory gets corrupted and my schedule table gets modified, or a link goes down. What happens to my system is not like the entire system is going to shut down, but rather there's going to be a slow and gradual behavior change in my design. So I want to understand what that is and how does that impact my operation of my system. Based on that, I can make decisions on increasing my redundancy. Maybe I can replace some of the components with components that have a higher mean time between failures. I can look at all of those kind of attributes in terms of the when I inject these faults and evaluate the failure. Now, this is on the system side. Now, let's take a look at the semiconductor side. The semiconductor side has a slightly different set of problems. At the transaction level, what you're looking at is, what is my bus topology? Which blocks do I, acquire IP from outside? Which ones do I build in-house? Do I just use an off-the-shelf processor like a RISC-V or an ARM or a Open Power or a ARC or a Tensilica? Versus, when I do my bus structure, do I use a network on chip, or do I use an AXI bus, or a network on chip equivalent from ARM, or I build my own proprietary bus with my own queue management system? How do I make those kind of decisions? Which is really what the transaction level model comes. So what happens is, rather than worrying about all the nitty-gritty details, exactly what happens to the pipeline in terms of execution units, or looking at the detailed flow of the matrix multiplication inside of a hardware accelerator, I'm looking more in terms of what is the sequence of things that might happen when an interrupt occurs, or I have certain periodic tasks, or I have some kernel operations. How does that impact my bus, my CPU, my memory, all of those subsystems, by varying all the different attributes of my design? So the idea here is that I'm not putting in every single implementation detail, but rather I'm putting in sufficient information about all the systems so I can try to come up with kind of a boundary of where my systems need to be. So I kind of have a high probability of comfort saying, okay, all of these are going to lie within this particular range, or should lie within this particular range. Could be CPU width, or it can be a processor speed, or it can be, like what's the maximum number of timers that I can have in my system. Now, once I'm done with that, I might want to start adding more and more details into my design. So like what I was showing you, where I took a more abstract system and then started replacing it with more detailed subsystems. So I want to start creating something that looks like this. I've got processors, buses, memories, I/O devices, bridges, all of this kind of thing, and then assemble up a system, define a behavior, define all my power, and then be able to run simulations by combining the three and looking at like what's the utilizations, what's the cumulative power, what was the latency for different types of tasks, being able to analyze all of those to go back and start modifying the hardware architecture. So for example, what I can do over here is like this component here, rather than running everything on my ARM processor, I want to take this and run it on a hardware accelerator, and then see how that will impact my system behavior. Will I still be able to meet my deadlines? Will I still be able to complete the required number of tasks that need to be performed, or the number of images or the number of frames that need to be processed within this time period? So now that I've started looking at more details where I'm actually having an accurate processor model, I have a detailed accelerator or an IP block model. Now I want to take it to the final level where I start putting in more cycle accurate. So what happens at every cycle by cycle, both in terms of power and in terms of performance. So you would have things like, for example, not just define the memory width, but also define, like in this case, the memory, looking at RP, RCD, RAS, looking at things like, for example, the WTRs, the RTPs, the WLs, the RLs, such that I can also start incorporating addresses into my system and feeding it in here, so I know exactly, okay, I've been bank 1, column, row 3, column 1, and then I'm going to go to bank 8, row 4, column 1, and it actually has CCDS, because they go across bank groups. So now I'm getting into extremely accurate details where my actual memory controller and my memory device could match up with my real with the system model. So I've taken it down to a level of accuracy that you can then incorporate into something that says, okay, this is exactly what my RTL is going to look like, or when I put it on a Palladium box, this will be exactly what the performance would look like. Now from here, a number of channels can be adopted for your system modeling. So for example, over here, you start off with the early architecture analysis, go into detailed design, and then you start doing debugging of your, while you're doing your development, but also be able to provide scenarios and test benches for your verification along with the expected results or expected outputs. So, I can give you my test vectors. I can say these are my expected output, or I can say these are different scenarios where we have seen corner cases, and here's what we expect as an output. So provide sufficient information for verification that you can then be able to accelerate your verification process, because you know exactly what are the areas you got to spend more effort on, what are the areas where you need to put more details on. So allows you to see an end-to-end design flow impact by incorporating this architecture exploration and connecting it down to the implementation flow. Now, one of the questions that's always asked is, do I just do things in isolation? With architecture exploration, you have the ability to bring all the different metrics of interest into the same environment. So for example, on the system side and my behavior, I might bring in that my redundancy is more important or security is more important. While on the semiconductor side, I might say, like I want to look at the memory access as being the most important thing. So my reads and writes are critical. So depending on what attributes are important for your design, the construction of your model, the type of analysis, what are the parameters that you would vary, will all go hand in hand. Now that we've seen, the demand, seen what are the applications and use cases, now let's go ahead and look at how does the methodology work? What does it mean to create a system simulation design? What is the effort in constructing something? So here I'm looking at 3 of these. One is at the stochastic level, the second is the platform model level, and the third is the power exploration level. Again, I know there's a lot of attendees, but it'll be nice if anybody has any questions. I know people have been asking some private questions, but you can always feel free to ask any of the questions that you'd want in terms of trying to understand this whole design or this methodology. Now, when I look at stochastic processing, what that really means is that it does not mean that my accuracy is not good. It does not mean that I'm being very generic. What it means is that I'm getting a much larger picture or a much wider scope of freedom to make changes. So in this particular case, what you would try is a large number of distributions or randomize the traffic that you feed in. Your different components may be defined as resources, can be passive resource or an active resource. The software itself is one where you want to have fairly good amount of accuracy, both in terms of what are the sequences of things that happen, but also, what are the delays associated with each stage and also with the transitions. So you want to have, the network with, for the different nodes that connect across, a subsystem, So for example, you can have your processing distributed across a network of components. And then you can start capturing things like, is the latency greater for the transfer or is the latency greater for the processing? What happens if I increase the buffer? Does that mean I can start doing more processing, or is it just that the latency increases and eventually the buffer is going to overflow? So to give you an idea of what that would encompass, say for example, you have a flow control or a traffic management in your system. So what you're looking at is, I've got multiple of these, input or ingress ports. And again, with VisualSim, you can define, as low as 1 or 2 to like 10,000 of these, connect them through a MUX, and you have a certain intermediate flow control. But the main flow control is really credit. If any of these channels have credit on the output side, it sends it out. If it doesn't have credit, it holds back and waits for the credits to be available before it transfers. Now, the scheduling algorithm of which queue to select is based on the arbitration that we provide. So it can be like a weighted round robin, or like a first come first serve, or any kind of proprietary technology. So what are the things you might be looking at here? What is the right algorithm, for example? How many queues can I handle? What should be the depth of these queues? What should be the rate at which I should be testing these intermediate flow controls such that it doesn't become a bottleneck. I still get my performance. What should be the maximum credit that can be allocated to each of these flows such that you still have 100% usage of the buffers here, but at the same time you don't start freezing them or locking some of the queues out. So a lot of dependent constraints start building up. So here's a model of that same design, traffic. These blocks here is where you have a parameter, in this case called ingress size, where you can actually describe the number of queues that you want to define. This here is, in this case, we're using a round robin. So this becomes the arbitration scheme. These are your intermediate queues with their own X on, X off trigger. And that's my egress. Now, one of the things that's critical is that, remember we talked about where I need to know what the credit available here is, and I need to lock out credit before I can start the transmission. What we've done here is, rather than having wires go back and forth and be able to measure the information and feed that back in, we have created these registers where this information is already stored. So for example, the register for this one could be egress. So then all I have to do here is go and look up that register and know what the value is, right from the script where I've written the logic for the arbitration, and then be able to determine which queue I need to trigger. So rather than having wires, or rather than having to like send a message, get an acknowledgement back, then the data, I just do a lookup, and then I can quickly get that information. Why is that useful? The biggest reason is that the speed of modeling. Rather than spending hours or even days and weeks trying to connect everything up together, I can do a quick lookup in my code. I have the answer. I can run the simulation. So model construction becomes very fast. And also, because I have all these predefined plotters and displays and histograms and a variety of other analysis tools, I can quickly generate. So in this case, for example, as you can see, these are my histogram of different latencies. This one shows me my buffer occupancy, and this one here shows me the statistics for the different ingress and egress queues. So one of the things it allows me to do, for example, is to see if any of them is going to have a buffer overflow, or if the delay exceeds certain threshold. So allows me to be able to get a quick idea as to where my bottlenecks are going to be. I start providing time schedules or data sizes or processing requirements. I define all of this in this level so that now I can feed this back over to the rest of the team to say, hey, this is where we need to be. This is what we can accommodate. If we go worse than this, you're not going to get the performance that you require. From there, we can start going into something that's extremely detailed. So this is what's called the platform model. The platform model would now, rather than using a distribution, you can say, you know what, I have some data from an old project, or I have a specific sequence. So rather than creating a distribution or just a randomized traffic sequence, I can now use a more realistic profile. Same thing on the system definition. Rather than using a resource like a quantity resource or an active or a passive resource, I replace that to say, I'm going to use a network on chip. I'm going to use a PCI Express. I'm going to use a Power 10 or use a Xilinx UltraScale MP-SoC, or use an Arring 653 operating system or a DDR5 with a HBM. So be able to utilize all of those and assemble up a complete platform model. And then the same task graph that I was running here for my software definition or my application definition, I can run the same thing. Of course, I might have to make changes. Like, for example, rather than a delay, I might say, okay, use this instruction sequence. Or for my memory access, rather than just saying, okay, here's the delay to memory, I can say, here's the address to memory. So it kind of replaces some of it, but the task graph is still the same in terms of what the flows and the behaviors are. Of course, for people that have highly distributed systems, you can have a full-fledged network with routing tables, adding bit arrays, buffers on the network, arbitration schemes. All of those can be incorporated to handle the network. So now, what is the difference in terms of the statistics? One is obviously you're getting far more accuracy. The second thing is you might have very specific profiling results that you might be looking at. For example, I might be looking at watts per memory access. So, if I'm doing 300 memory accesses, how much is the power consumed? Versus if I'm doing like everything locally with a hardware accelerator and I'm using a block RAM, versus I go get the data from an external DRAM. How does that change my performance, or how does that change the power profile of my system? So talking about a platform model, it can look something like this. So this is my task graph. This is my hardware accelerator. I'm sorry, my processor. These are my tables that maintain all the details about my application itself. So you can see the different types of resources that you can define in your system. So now results are also different. So I get the MIPS. I'm getting my instantaneous and active power, end-to-end latency. So you can see where it went below the deadline, where it exceeded the deadline. So it's like it's an inverted number. That's why you're seeing one's higher than the other. But you can also get details like, on the bus, what was the input buffer occupancy? Or for example, on the PowerPC, what was it, for the iCache, what was the maximum delay? Or what was the DRAM utilization? And how much was the throughput through the DRAM? How much was the power, the accumulated, the average power for each of the devices? What was the max, min, and mean MIPS on the particular design? So it gives me the ability to start looking at extremely detailed and extremely accurate information about my subsystem. So if I go back to one of the designs that we were showing you earlier, which is the Zinc, the UltraScale MP-SoC, when I go ahead and run this, I'm just going to focus on this one here. What I have is I've got a series of programmable logic functions that are executing things at the same time or in conjunction with the with the processors that are within these MP-SoCs. Now, one of the things that we have over here is that you have all these different interfaces from the programmable logic to the AXI bus that then connects to the DDR. So these are like, some of them are fast connections, there's the high speed, there's the medium or moderate, and then there's the low speed connection. So depending on, what you need for each the programmable logic, it can be connected to one of those different interfaces, and then those are sent out to memory. Now, when I start looking at some of these statistics, I'm not using the second process, so you don't see some of these things. But to give you an idea here, I get to see what was the response time on each of the cores for the different tasks that are executing. Similarly, I can see what's the total response time for the entire task itself, which is the task graph. So this is a sequence of things. So if you notice, many of these points are right here, but you're starting to see a lot of spikes. So this one finished at 440 microseconds, while this took about 55 microseconds. So fairly large range. So you want to understand why you have such a huge range. Also, at the same time, you're also looking at, for example, here we go. We're also looking at the power consumed by the FPGA as well. So you can see these are all my individual spikes. If I go into one of these, you can actually see two things. One is, what is the time duration, the width, the amount of time it's been in a different state versus, it's been a lower state, or in this case, a standby state. Similarly, you can see when it gets down to the lowest state possible. So this is not just for one component within the FPGA, but this includes all the buses, the memories, the processors, and the programmable logic. So you can actually cover the power consumption for all of those subsystems to kind of give you a gauge right up front as to what your performance and power consumption trade-offs are in your particular design. So now looking at the very last aspect, which is the power, architecture exploration with power consumption is probably one of the hottest technologies or capabilities that's available. The reason that it's very critical is because today most designs are not very power friendly. So either they're consuming too much power, or the requirements to battery and to the photovoltaic cells are pretty high. So we want to cut some of those things down. What it allows you to do is, you can look at a state-based power analysis. So for example, as different devices move into different states, their power gets modified. Now, it can also be that the power in each of the states is dynamic. So it might actually be based on a combination of LDO efficiency, area, switches turned on, different kinds of attributes. But you can also have different states for these power subsystems. You can have a power management algorithm to say when you want to turn it off or move to a lower power state. Also, for much larger designs, you can even incorporate the power generators or the energy harvesters, connect them to a series of batteries that are available in the tool, and then you can look at your consumptions, and you can look at how the management works and things like that. So to give you an idea how that works, in today's world, if you take any design, you'll specify, here's all the different devices, these are the power in different states. You'll take in the cycles, then you'll put them as being, like an average of all of these, and you'll get a single number. Now, what you notice in VisualSim when you actually put in a very detailed model is that, yes, so you do get that average thing at some point, but then it very quickly, goes and optimizes or into a certain power level where it starts becoming more stable. So the power is not just based on a computation of the average values, but it's based on the use cases, the traffic, and when things are more dynamic in terms of the actual power within a state. So as a result of that, you get very high accuracy on the power consumption. So why invest in architecture exploration? So we saw the reasons for it. We saw the types of applications. We saw the methodology. But why invest in it? One of the major reasons for the investment in architecture exploration tools, one is, of course, model construction time is very low because of the large number of IPs available. The second thing is really about the analysis. You can do a large variety of analysis before you schedule any sort of implementation. So you're defining your specification very early in the design process, so that way your implementation gets to become more solid. So if you remember, the first thing I mentioned was that you're eliminating all your surprises during integration. So you want to weed out all the possible bugs and all possible errors right up front without having to wait until you get to the implementation phase. So what does this do for me? Accelerates my model development. But second thing is it creates a highest quality product. What happens when you find problems during your implementation? You try to apply patches, you try to apply fixes. But in this case, because you found everything up front, you're not creating those patches or fixes. You're just going through a complete product development phase with minimal rework. So it creates a high quality product, which is what you originally wanted is what you're getting now. The other reason for doing it is because you can save yourself a substantial amount of time. We've done a lot of research, and these numbers can be in the range of 25 to 30%. It's substantial savings in extremely complicated systems, even more acute when you're in completely unknown chartered territory, like for example, doing a completely new design, things like those. So what it allows you to do is it gets you a higher quality product. It cuts down your product schedule. The third thing is potentially, because you're getting to market faster, your amount of resources used is lower, you actually increase the amount of revenue per project. So with this, I would like to conclude my presentation today on this webinar of making early architecture decisions using system level simulation. I hope you've got what you were looking for in terms of the application and the use case and how you can benefit from it. I'm still open right now to answer any other questions, so feel free to click on the chat window and I can answer your questions. Also, I sent you an email with my introduction and also the invitation, so feel free to connect with me in terms of asking any questions. You can also do it on the private via email as well. So at this stage, I'm going to open it up to any questions that people might have. Of course, we've got a huge number of FPGAs. Let me move over to the list of libraries. Now, one of the things we've been focusing on more recently have been the new generation of FPGAs. So we have, the Xilinx, Zinc, Vertex, Kintex, the Stratix, and Arias, and also Smart Fusion from Microsemi. Many of these are some of the latest generation, but we also have some of the older generation, like say, for example, the Vertex 5s, the Vertex 4s. Also, we have like some of the Zinc 7000s and things like that as well.